Hey everybody, so in this video I'm going to be talking about quantum numbers in chemistry. So there are four quantum numbers. You have n, then you have the L, and then m sub L, and then m sub S. So what these four numbers mean is that, so let's start with n. So for n, it's also called the principal quantum number, and you would only see numbers of integers starting from 1 and then 2, 3, going up. The most common ones you would see are 1, 2, 3, and 4. So no 0. And then, so this describes the size of the orbital, the distance away from the nucleus. So this describes the size of it. And it also tells us the energy level. So if you have four, remember the Bohr atom, you have the nucleus in the center, and then these are the shells, with the valence shell being the outermost. So it tells us how many energy levels there are. If you have four, that means we have four energy levels, and as a result, you would have more energy. So, and then moving on to the L. So the L quantum number is telling us the type and shape of the sublevel. So you have okay, so the numbers start from 0 and they move up um, by increments of 1. So 0, 1, 2, 3, and so on. But this number has to be at least 1 less than n. So if you have n being equal to 3 for a specific orbital, then L is restricted to only a maximum of 2. So the L could be a 2, a 1, or a 0. It can't be equal to it or greater than. And so the shape, so if you have, so 0 corresponds to the letter S, 1 corresponds to P, and 2 corresponds to D, and 3 corresponds to F. So the shape of the S looks like this, just a sphere. And the shape of P, they usually characterize as like a dumbbell. And then D is like a clover leaf, so something like that. And there's also another exception to the to D when L is equal to 2. It looks something like this. So kind of like a dumbbell, but with a ring in the middle. Okay, and then for F, it's a really weird looking shape. I'm going to attempt to draw it something like that. 4, and then you have another 4 on the bottom. But just to recognize, just to visualize it. Okay, and then the M sub L. The M sub L, it's the magnetic quantum number. And then, so depending on whatever the L is, the ML is a range of positive L to negative L. So let's say L is equal to 2. That means M sub L could be from negative 2 all the way to 2. In between would be negative 1, 0, 1, and 2. It's like a set. If M sub L was equal, if L is equal to 0, that means M sub L is only 0. If M sub L is equal to negative 1, if L is equal to 1, then M sub L is negative 1, 0, and 1. That set. Okay, and then M sub S, you always have, no matter what those other numbers are, you always have either positive half or negative half. And they just represent the spin of the electron. And that's it. So let me just give you like an example of something. Let's say, for example, you were asked if a certain quantum number is valid. So let's say, for example, we have 4, oh no, how about 2D? Is this allowed? So first of all, this number is the M and D is the L. So L, remember when I said S means 0, P is 1, D is 2, and F, wait, I'm running out of space. Remember when I said S equals 0, P is equal to 1, and D is equal to 2, finally F equals 3. So D corresponds to 2. That means we have N and L equal to each other, and remember when I said the N can't be equal to L, but at the same time also N can't be, so L can't be greater than or equal to L. So N is always greater than L. So this is not valid.